So 31 times 6.8 repeating, which is something absolutely magical. What is it? 10.8. So the vehicle travels 210.8 meters to stop, and then it cuts back. Be nice for some contrast. Let's see how well red's working today. So 210.8 horribly from there to there. Well, if he ends up 170 meters from where he started, I can just subtract the two to figure out how far this is. There are other ways of doing it, but one way of doing it is just, well, I know I go 210.8 meters that way. I end up 170 from where I started, so this has to be the difference between the two, which is 40.8 meters. And so the distance traveled, 210.8 plus 40.8.
You say again?
Who asked that? So,
Can you say it again, what you said?
all right, so the distance traveled, I traveled 210.8 meters to get to the stopping point, and then I traveled 40.8 meters back. So the total distance is just 210.8 plus 40.8. Now, some people, the brain just isn't working that way at the time that they're using it. When they're doing this, that's what I meant. So, alternatively, and this is just a different way of doing it, I know the entire trip is 6 seconds. Sorry, 10 seconds. So that means, since I stop at 6.8888 seconds here, and I end at 10 seconds here, this time right here has got to be whatever time's left over after that. So that's 3.1 repeating seconds. My average velocity for this segment right here, well, it's the average of 0 and negative 28, which is negative 14. So the distance I'm traveling back would be 14 times 3.1 repeating, which I'm hoping is 40.8. But I don't think it is.
Where'd you get 14 from?
The average velocity going from 0 to negative 28. 7.6, so yeah, there's a number off somewhere. Is this?
I think it's that one, the two, because I got 214, because they said it was repeat, right? So,
Yeah, so you got, here you had
214.
214. With the 8 repeating?
Yeah.
Okay, so that would make this, that's an extra 4 there, so that's 44.8. That would make more sense, okay. 14 times 3 is 42, so that's why I knew 40 seemed off. And so multiplying those together, you should get 44.8. I don't think that's easier, it's just, it's on the way your brain's working at that moment.
Wouldn't it be neg? Yeah, nothing.
It is negative, I basically did negative displacement here,
Yeah.
but the distance is the absolute value of that.
Yeah, yes.
And a little pro tip here, if you have an object turning around, the distance traveled is not the absolute value of the displacement. The answer is not 170 meters. Distance is the magnitude, is the absolute value of the displacement, only if you don't turn around. Other questions? Yes, Genesis.
I have a question from the master set, 405. With the dog, the ramp pushes up and right on the dog with a normal force of 21 newtons. The dog would push down and left on the ramp with a normal force equal to 21 newtons?
It would be the same magnitude, opposite directions.
Yeah.
Yeah.
Okay, just wanted to make sure.
Okay. Other questions?
I've never understood the push-up question, because I did get it wrong.
Ah. Oh, the arms don't bend that way. All right, so if we look at the forces acting on the person. And train, and then ground. So what are the forces involved in person-ground interaction here?
Wait.
All right, that's it. Very similar to the elevator problem. If you are moving upwards and speeding up, then acceleration is upwards. Again, they're the same sign if you're speeding up. If you're slowing down, your acceleration is downwards. If you're going down and you're speeding up, your acceleration is down, and if you're slowing down, acceleration is up. So same sign speeding up, opposite sign slowing down. In that particular problem there, you had I forget what the wording was. So man gets into push-up position, starts his daily exercise, he pushes on the floor and moves upwards. While moving upwards, he speeds up and slows down. So while he's moving up and slowing down, so moving up tells me velocity is up, slowing down tells me acceleration is down. So if he is, so now I know the direction of acceleration. The question then goes on to, he pushes on the floor with 240 pounds of force. So which of these forces is 240 pounds? No.
No.
He's pushing on the floor with 200, which of these forces is his, because he's pushing on the floor?
Normal.
Wait. That'd be the normal force. This is 240 pounds. Which means this is also 240 pounds. This is what the problem gives you, that he pushes on the floor with 240 pounds of force. By Newton's third law, this also has to equal the same. And so then he asks, then the question is, the force with which the earth pulls through gravitational force, in other words, his weight, the magnitude of his weight, is less than 240, more than 240, or whatnot. We've established the acceleration is down. Therefore, looking at the two forces acting on him, weight must be bigger than the normal force. So therefore, his weight would have to be greater than 240 pounds.
Can you explain why weight is more than the normal force again?
The net force has to be the same direction as acceleration. Once we accept that acceleration is down, I have only two forces acting on it. If acceleration is down, it means the net force is down, which means weight has to be bigger than the normal force. Take it to an extreme. He's doing push-ups and he sort of pushes himself off the floor. He's definitely going to slow down then. So it's because the weight is much bigger than the normal force. But actually, if he pushes himself off the floor completely, his normal force is 0. If he's not touching the floor.
Yeah.
Sorry,
Thank
you were
you.
processing.
Yeah.
Other questions? I look forward to tears of joy streaming down my face as I grade the tests. Not quite done yet, we still have 10 minutes.
Thank you for.
Yeah. We last left off. What was last? We were doing energy, right? I'm boring the classes again. I know we did momentum.
We were doing energy.
We were doing energy? How far did we get with energy? Oh, we got to defining work.
Yeah. We did kinetic energy, potential energy, and we defined work.
That's right, we did the problem of the object falling.
And then conservative and non-conservative.
Okay. Did we do the, how fast is an object going after it falls 20 meters?
Yeah, we
Okay.
did.
Did we do the ski slope?
No.
Why is it so weird?
All right, we have skier. I'm going to assume that the snow is frictionless. The question is, how fast is that skier going when he gets to the bottom? I'm not asking for the final velocity, I'm asking for final speed. This is a conservation of energy problem. So let's start out with some basics here. When the skier is here. What are the forces acting on the skier when the skier is at that point?
Did you say it's frictionless?
It is frictionless.
Weight.
Normal force.
This is the two. So we have weight acting down and normal force acting that way. Sorry, I think you said weight and I thought you meant the other kind.
The question.
So we have two forces acting on. Is weight conservative or non-conservative?
Conservative.
Yes, it is. Normal force, conservative or non-conservative?
Non-conservative.
All right, so potentially we don't have energy conserved here. So let's think about it a little bit more. I know that the work is force times displacement. If we went through the whole bit with the dot product. So at this moment, when the normal force is that way, in which direction is he moving? He's going, normal force is at an angle, you're saying he's also going that way?
No.
Which way is he going?
To the right.
So the normal force is perpendicular to his movement at that moment. Matter of fact, throughout the entire trip, the normal force is perpendicular to his movement the entire time. So since that normal force is perpendicular to his instantaneous force is perpendicular to his instantaneous displacement, what is the work being done by the normal force? Doing a dot product with two vectors, thank you, Angel. Yes?
Zero.
It is indeed zero. So the work done by the normal force is zero, because the normal force is perpendicular to the displacement throughout the entire trip. No matter where whatever direction the normal force is pointing to, its displacement at that moment is perpendicular to it. So therefore, the only force doing any work is its weight. Therefore, since it's a conservative force, energy is conserved. What does conservation of energy mean?
That force changes energy from one type to another.
Okay, that's what a conservative force does. What about the general concept of conservation of energy?
Say it.
The final impulse and the initial impulse are equal.
The final what?
Impulse.
Not impulse.
Uh,
I think you're mixing two things there. You're along the right track, but wrong word.
Is the balance between the
Oh.
forces?
Really less fond of that one, because that's not necessarily true in this case.
Total energy stays the same.
Yeah. Your initial energy equals the final energy. Conservation of anything in physics, different than what you have than conservation laws in, say, ecology. That's just trying to preserve as best you can. Conservation in physics is whatever you start with is what you end with. So my energy initial is equal to my final energy. What are my two types of energy?
Kinetic and potential.
All right, so I got my kinetic energy plus my potential energy. It's equal to my kinetic final plus my potential final. What is the formula for kinetic energy?
Which one?
All right,
Is it that 1/2,
keep going.
1/2 mv squared?
That is the one. Let's try that again. What's the formula for kinetic energy?
1/2 mv squared.
That was a refreshing thing. 1/2 mv initial squared. What's the formula for potential energy?
Which one?
There we go. The one associated with weight.
MgH plus C.
Yes, and you can just stop at mgh. The plus c is just gonna allow us to justify where we can put zero. But mgh initial is equal to, well, the same thing, it's just final. 1/2 mv final squared plus mgh final. All right, this is just generic steps. We'll eventually, probably have to wait till next week, but eventually we'll throw in another different potential energy. Are any of these equal to zero? So I don't know while you're reading my mind, which answer it will be. Let's go through. First off, what does this V represent?
Velocity.
Speed.
Speed, the vector symbol over it. Is his initial speed zero? It's supposed to be. I didn't actually state that, but yes. So this is zero because the initial speed is 0 meters per second. And let's just make it official and pretend, despite the fact that it's been recorded, the initial speed equals 0. We'll pretend it's been there all along. Okay. Is the initial height 0? Okay. Is the final speed 0?
Yes.
If you went down a frictionless hill, would you be going 0 at the bottom?
No.
You would not. No, this is what we're actually trying to find right there. Is the final height 0?
Yes.
Yes.
Why?
Because you're,
No, that's not the reason why.
no.
That's how hills work.
That's how what works?
That's how hills work.
And you haven't been in that room where you put the thing on the track and it goes uphill? What is amusement things in Tennessee? And if you listen to the internet, no one knows how those things work. I'm fine with this being 0. But again, the question is why? Because each of us is mighty. Okay, Johanna, you're about to reveal?
Because we say it.
Yes. We can set h is equal to 0 wherever we want. If you want h to be 0 at the bottom, that's fine. And the reason it's 0 at the bottom, because we say so. Now, you might have ulterior motives if that's how hills work. Or that's the ground and you want to make that 0, that's fine. That's your own personal scars and memories. But in physics, we can set h is equal to 0 wherever we want. And apparently, the desire was to put it there, at the bottom. So now I'm left with just mgh initial equals 1/2 mv final squared. Plug and jug, or can we simplify it one step more?
Can't solve the m's.
Yeah, I have mass on both sides. I didn't tell you a mass, that one was on purpose. If you are uncomfortable with that, just make up a mass, not 0. 1 is a nice number, but not realistic for a skier, I would hope. A 2-pound man, skiing down the slopes. All right, so now we're left with g times the initial height is equal to 1/2 v final speed squared, and so multiply both sides by 2. You can plug in numbers at any point that you want, but I know people deep down inside would rather just look at letters on the board than numbers. So